In this video, we're going to talk about the mole and then also molar mass. First of all, the mole is a unit of measurement. It just describes how many of something you have. And it's very similar to some of these other units of measurement, where a dozen, right, typically means 12 of something. A couple, depends on the context, could be 2, 3, possibly 4. Again, depends on the context. If you said, I'm going to meet my friend in a couple of hours, that doesn't necessarily always mean 2 in that context. A ream just means 500 of something. Most commonly, that is used in paper. Paper is sold by the ream. So you buy a pack of paper, typically 500 sheets is 1 ream. And a mole just happens to be 6.02 times 10 to the 23rd, which is very large. And that's primarily why it's used solely in chemistry, because atoms and atoms, molecules, formula units, they are all incredibly small. So in order to describe something, we typically need to use the mole. So how big is it? Right, it's basically 602 followed by 21 additional zeros. So it's sometimes unfathomable as far as how large it is. But just to put things in perspective, if you had a mole of basketballs, which would be very difficult to obtain, obviously, but you'd create a new planet the size of the Earth. Likewise, if you had a mole of ping pong balls, you could make a 60-mile thick layer covering the entire surface of the Earth. And here you kind of have Mount Everest as just an idea of what that might look like. And if you're born with a mole of pennies, which would be a lot of pennies, you could spend $1 billion per second. And if you lived to the age of 80 years old and didn't invest your pennies in something like crypto, you would have pretty much the original amount left. Now, when we're using a mole represents particles. And there's a bunch of different particles depending on what type of material you're referring to. So atoms represent elements. Right, so that would look like sodium, sulfur, copper. Right? If you have this many atoms of copper, you'd have 1 mole of copper. Now keep in mind, some elements are diatomic. So there can be a little bit of confusion amongst the diatomic elements because, for example, if I'm looking at bromine, well, you notice that Br2 itself is a molecule. But what type, what is the smallest particle that represents the element itself? Well, it's the bromine atom. Okay, so sometimes the diatomic elements can provide a little bit of difficulty or confusion because, yes, Br2 itself is a molecule, but the smallest particle that represents bromine is the atom of Br. Okay? Molecules typically represent covalent compounds. I'll just update this, that if you're talking about elemental bromine or elemental oxygen, or if you're just talking about the diatomic elements from an elemental perspective, yeah, the smallest particle that represents that element would be the atom. Molecules, however, represent covalent compounds like water, CO2, CO, or, again, if you're talking about Br2, like we said up here, this itself is a molecule. All right, let's not get that, don't forget that Br2 is a molecule where if we're talking about elemental bromine, then what Br, even though Br is not going to be found naturally just by itself. It will be in this form. You have this many molecules of water, you have 1 mole of water. And formula units represent ionic compounds like sodium chloride, copper 2 sulfate, calcium sulfate, anything of those things. And roughly, if you have 6.02 times 10 to the 23rd formula units, right? That's the abbreviation we use for formula units. You have roughly 1 mole of calcium carbonate. And lastly, ions are just defined as an atom or group of atoms with a charge. Like sodium ion, or calcium ion, or sulfate ion, right? Those, you had 6.02 times 10 to the 23rd sodium ions, you'd have a mole of sodium ions. Now, we look at this. And yeah, notice we've got a shadow coming in. We'll just kind of deal with that due to where the sun is. But if we want to figure out what is the representative particle that represents this, well, that's an ionic compound, so that's going to be a formula unit. The representative particle for Cu, well, that's an atom. Br2, well, again, this is where context is somewhat important. If you're talking about just bromine from an elemental perspective, right, that's an atom. But if a problem is asking you about, well, how many molecules of bromine, well, then it's referring to the Br2. So I'm just going to put both these here. However, just keep in mind, if we're talking about elemental bromine or any type of diatomic element, the smallest particle or the representative particle of that element is an atom. But they do exist in nature as the diatomic molecule. S2 minus, well, that's a sulfide ion. Well, that's an ion. And then lastly, CO, that is a molecular compound, which is a covalent compound, and that is a molecule. Now, moving on to molar mass. So when dealing with chemical reactions, the mole is the desired unit of measurement. We can do a lot of things and a lot of calculations, a lot of understanding of how chemical reactions work, and so on and so forth, if we have the amount of moles of our substances. Whereas grams, mass of something or volume of something is not as useful, but its utility is being able to convert those quantities into moles. So we don't have scales or instruments that can just determine moles of a specific substance directly. We have to do those calculations kind of manually. And just as a definition standpoint, a molar mass is just defined as the amount of grams in 1 mole of a substance. And we can use our periodic table in a different way because earlier this year, when we were doing average atomic mass, the units on those atomic mass values from the periodic table were AME, or atomic mass units. Right? That is a very microscopic type of approach. We can also use that atomic mass from a macroscopic point of view, in the sense that the atomic mass of an element is expressed in grams, is simply the mass of 1 mole of that element. And what does that mean? Well, for example, magnesium, is Mg. If we want to know what the molar mass of magnesium is, we just need access to your periodic table. And if you look on the periodic table, you notice that the atomic mass of magnesium is listed as 24.31. Well, from a macroscopic scale, that means if you have 24.31 grams of magnesium, that means you have 1 mole of magnesium. Right? And basically, this is a conversion factor that we'll use to go from mass of something to how many moles of that something we have. You'll also see molar mass written. For example, the molar mass of magnesium will also be written like 24.31 grams per mole of magnesium. And either of these, either this way format or this format, represents the molar mass of this element. People get confused when they see this. 24.31 grams per mole. Remember, it just looks like this. It's just saying 1 mole is the same as 24.31 grams of magnesium. Much like any other conversion factor we used earlier this year, like 12 inches is the same as 1 foot. And you may see this used either as 1 foot over 12 inches or 12 inches over 1 foot, depending upon what you're trying to convert to and from, which is coming up next. Okay? Likewise, if we're talking about the molar mass of oxygen, well, if we're talking about oxygen gas, right, that's going to be 32 grams per mole for O2. But if you're talking about just elemental oxygen, like if it's part of a compound, well, the molar mass of a single oxygen atom is 16 grams per mole. So it depends on, when it says what's a molar mass of an oxygen or diatomic element, you kind of need to think about, well, in what context do we care? Then if we're doing a compound here, we need a formula. Sodium chloride is NaCl. It means you got 1 sodium and 1 chlorine. So to get the molar mass of that, you just have to add these two things together. You have to add 1 sodium and 1 chlorine. So the sodium from your periodic table, 22.99 grams. Chlorine is 35.45 grams in 1 mole of each of those. Add these two together, you get roughly 58.44 grams per 1 mole of sodium chloride. Again, you can also write it in this form. 1 mole of sodium chloride is equal to 58.44 grams of sodium chloride. And if you're confronted with something like this, glucose, and you're given the formula, C6H12O6. Right, the one thing you don't do is just take 1 carbon, add it to 1 hydrogen, add to 1 oxygen, and say that's your molar mass, because that's not true. Right, you've got to take these subscripts into account. So to find the molar mass of this compound, you've got to add 6 carbons together with 12 hydrogens and 6 oxygens. So the carbon is going to be 6 times 12.01 grams, or roughly 72.06. Hydrogen is going to be 12 times 1.01, which is mass of a single hydrogen, 12.12. And the oxygen is going to be 6 times 16, roughly 96 grams. So we add all that up, and you're going to get roughly 180.18 grams per mole for the molar mass of glucose. Again, you can write that as 1 mole of glucose is equal to 180.18 grams of glucose. And just keep in mind, significant figures for these, you can have as many significant figures as you want, because these are all coming from the periodic table. None of this was measured by any type of equipment. Lastly, was a molar mass of chromium 4 chlorate. Key thing here is you've got to have the correct formula. And then chromium, got one of those, and that's 52.06 or 52.00, depending on the periodic table you're using. Keep in mind, there can be some variation depending on which periodic table you're referring to. Obviously, your periodic table, your blue one or the pink one, is what you're going to be most accustomed to. But just notice, if you look at other periodic tables, there may be slight variation in molar masses. You got 4 chlorines, So that's going to be 4 times a 35.45. And then you've got 12 oxygens to take care of, because you have, remember, 4 chlorates. So that's 52.06. This is 70.9 times 2. Well, the chlorine is about 1141.8 grams. And this is roughly 192 grams. So a grand total of around, right over here, 385.86 grams per mole for chromium chlorate, 4 chlorate.